Hello and welcome to the AP Physics C Mechanics Review Guide. Today I'm going to be covering the Physics C 2024 Set 1 Mechanics Free Response questions. So yeah, let's just hop into it. I'll be explaining each question and the thought process behind it. So block A of masses, or block A and block B of masses m and 3m respectively are arranged in a setup consisting of an ideal spring with spring constant K and horizontal surface. Friction between the surface and the blocks is negligible except in a region of length d, where the coefficient of kinetic friction between block A and the surface is mu. Block B is attached to a string of length L and negligible mass, as shown in figure 1. Block A is held against the spring compressing the spring a distance xc. So this has a force on it already, right? So that's fine. At time t equals 0, block A is located at position x equals x naught and is released from rest. So after the block is released, the following occurs. T equals T1. Block A is at x equals x1 after traveling a distance xc. Block A moves with a speed v, and the spring is in its equilibrium position. Okay, so I'm just going to label my x1 T1, right? At time t equals T2, the left side of block A is at x equals x2 after passing through a distance d across the region with non-negligible friction, right? Okay, so that's after it's gone from here to here. Here's T2, right? And now at time t equals T3, block A is at x equals x3, and block A collides and sticks to block B. Okay, so here's where the collision happens, T3. Amazing. Okay. So let's go back here. So for parts A, express your answers in m, k, d, mu, and x compressed, and physical constants as appropriate. Okay, derive an expression for the speed v of block A at a time t1. So we know that at time t1, there's no friction here. Oh, I wrote mu weird. So there's no friction, so we don't need to worry about that. We just need to worry about energy, right? Because it had energy here, right here it has spring potential energy, but when it reaches its equilibrium, let me draw that line, which is right there, all it has is kinetic energy. Because if the spring is in equilibrium, its compression distance is 0, and you know the block can only have kinetic energy. So let's do that. So let's use conservation of energy. E final has to equal E initial, right? So the initial energy was, I don't know what just happened there. US has to equal the kinetic final. And let's write the equation for both of those. 1/2 kx squared, well, x is xc, 1 equals 1/2 mass mv squared, right? Let's cancel the 1/2s. Bring that up here for k xc squared equals mv squared. Now I'll just divide by mass in order to get v by itself, v squared by itself. And now I can solve by taking the square root, right? So this gives me, I don't know why I drew my x like that, kxc squared over m. The square root is equal to the velocity at the end. Just box that up nice and neat. Great. Derive an expression for the speed VAB of the two-block system immediately after the collision at time t3. So the block has basically had its kinetic energy, and now it's moved through this region of non-negligible friction with coefficient of friction mu. So if it's being acted on by the force of friction and there's a distance d, I'm going to think work, right? There's no time, otherwise I would think impulse. Well, there is time, but we don't have numerical time values that we can work with. So we're going to have to use work because we're allowed to express things in terms of d, right? So we're going to think, okay, the work has to equal the change in kinetic energy, which is going to give me the final velocity of the block once it's moving here before the collision. Then when we hear collision, we're going to think conservation of momentum, right? So let's go down here. So let's use the work energy theorem to get the final kinetic energy. So work has to equal delta K, and that's work done by the force of friction. Now let's figure out what the force of friction is. Well, the sum of the forces on the y. I'm just going to do this one really quick because AP kind of wants you to have this memorized. But yeah, so some forces y, Fn minus Fg equals 0. Fn must equal Fg, which is mg. Great. The force of friction is equal to mu Fn. And since I know Fn is mg, I'll say that's mu mg. Done. Right? So now work is F dot D yielding F friction times the distance d cos theta between the two. Now this cos theta is going to be negative, and I'm going to show you why. So here, I'm going to visualize the block right here. So the force friction is acting that way, right? Because it opposes the direction of motion. So I'm going to label this FF. But our displacement is this way. This is how we're traveling. That's delta x, right? That's where d is going. So the theta, the theta between these two is 180 degrees. And cosine of 180 degrees is -1. So that's going to give us negative FFD. And FF is just mu mg. So now I'm going to write the work is equal to negative mu mgd. Right? So now I'm going to start doing the kinetic energy part. I'm going to split this off here so I don't go into the momentum part. So now the kinetic energy, the change in kinetic energy, since our mass is not changing, I'm going to write 1/2 m delta v squared. Right? So I see two things that I can cancel. Well, mass is here. I can cancel mass on both sides. And 1/2, if I multiply 2, then I can just get rid of that 1/2 there, because I really don't like fractions. So now I get 2 mu gd is equal to delta v squared. And what's delta v squared? Well, that's equal to v squared final minus v squared initial, right? Don't get this confused. This is not equal to v final minus v initial squared. Do not make that mistake. I've made that mistake before. It's cost me so much. Do not make that mistake, right? So now we're going to rewrite this, subbing in for v naught squared, because v naught is the initial kinetic energy that it has, which was this velocity, right? That velocity corresponds to the kinetic energy it has before it enters the friction region. So now I'm going to write it out. -2 mu gd equals v final squared minus, and v naught was square root kx over m, or no, kx squared over m. So that squared is just without the square root, so we're going to write kxc over m. Oop. Great. So we're done with that, right? And now I'm going to solve by putting this on the other side. So I'm going to write kxc. So I'm going to basically add, so I can cancel this here. Minus 2 mu gd equals v final squared. And now the way I solve for this, oh, sorry, I forgot the kxc squared. Forgive me. I'm going to take the square root, because v final squared, in order to get v by itself. So 2 mu gd equals, that is a little excessive there. I'm just going to take that. Oh, no, it's not. Okay, never mind. Equals v final. Great. Now I'm not done yet though, right? I have the velocity v final, which is, I'm going to write this as v naught a. That's the velocity of a after it's exited the friction region and before the collision. So now I'm going to go to the collision part. So these two blocks, let's just visualize them. This is traveling with v naught a, and it hits and it sticks, because this is m and 3m, and now they're moving with some velocity vab that we're trying to solve for. But because it said sticks, we can think that it's an inelastic collision in which momentum is conserved. So let's think. Momentum initial has to equal momentum final. Now, I know that it said block 3m was at rest before the collision. I'll just visualize that as well. So here's 3m. And its velocity was 0. It's not moving, right? So it has no momentum. So the only initial momentums, or momenta, I need to consider is mv naught a. So now mv naught a has to equal the momentum at the end. Well, if the blocks are moving together as a system, then I have to add their masses, because they're moving at the same velocity, vab. Right? Now I added these because they're together. They're stuck together. I add them, and this, you could write them as their own individual momentums, but you'll end up combining them anyway because they move with the same common speed, vab. Right? So now I'm going to rewrite this as mv naught a is equal to m plus 3m is just 4m vab. And now I can cancel m here, right? So cancel this, and solve for vab by saying v naught a over 4 equals vab, right? But I'm not done yet, because what did it say I could use? It said I can use m, k, d, mu naught, or mu, and xc. Well, V naught A is not something I can use, so I have to sub in what I got over here, right? That's the whole reason why I went through this whole energy thing. So I'm gonna sub that in now. So I'm gonna say square root kxc squared over m minus 2 mu g d divided by 4, right? That's what it was. Yeah, is V naught A has to equal the velocity of the two block system after it's done. And now this is my final answer, right? I can leave it in that form. So let's move on to the next question. So on the following axes, sketch a graph of the kinetic energy K as of block A as a function of time from t equals 0 to t equals 3. Okay, so what I need to do here is I need to think, okay, kinetic energy. What's my kinetic energy equation? So that would be 1/2 mv squared. That's horrible handwriting, forgive me. 1/2 mv squared, and I just wrote the same thing again. So k of t equals 1/2 mv of t squared, right? This is what you need to remember. So now let's consider the motion, right? I'm so glad they gave us this diagram. Sometimes they don't. So when the block is here, right, and it's moving this way, its velocity cannot be described as linear, right? So this can't be described like this. It can't be described like that, right? Because the velocity is not linear. If you remember, this is Unit 7, oscillations of the new curriculum, but the block undergoes simple harmonic motion because it's attached to the spring. So we know simple harmonic motion, cosine describes x, and since there's no phase shift, the velocity is sine. It's represented by sine. So we need to think if sine of t represents the velocity, then sine squared of t has to represent the kinetic energy, because these two are constant multiples. Sure, they'll shift the graph up and down, but we're not asked with like respect to a horizontal asymptote, so that won't matter. So I'll put an image up on the screen, but I'm going to look at Desmos to see what sine squared looks like. Sine x squared. Right. So sine x squared never goes below this axis. Never, right? Because it's squared. And it looks kind of like this. Oops. Looks kind of like this, right? So this is where the max kinetic energy is reached, and that makes sense, right? So all you need to realize, simple harmonic motion. What are my simple harmonic motion equations? Okay, it goes cos, sine, back to cos for acceleration, right? So now this is the kinetic, oh, that's horrible. This is the kinetic energy I have. Now from T1 to T2, we need to think acceleration, right? The acceleration caused by the force of friction is constant because mu is constant. So we know if A is constant, then the A graph looks like this. So the velocity graph should look kind of like that, right? Because you're starting at some initial velocity and you're decreasing. Well, now if you were to plot negative x squared, right? This squared would yield this graph. This is what I want. This is what I want you to realize. This graph squared yields a graph that looks kind of like this. Oops. Like that. Because it's not decreasing linearly due to the squared part, but it is decreasing, right? So it will decrease something like a parabola. Actually not concave down. That's my fault. So you'll think x squared, and you'll basically make that negative. So it's going to decrease something like this. Oops. Something like this. And it's going to reach, it is concave up actually. So it's going to decrease like that, right? Because A is constant and it has to decrease and it has to flatten out, right? It's not going to, because the difference between that graph and this graph is if I plotted it like this would be wrong. This would be saying my kinetic energy, right? Sorry. This would be saying there's a lot of power going into it. The acceleration would be increasing, in other words. So don't say that. Because the kinetic energy, right, this is the magnitude, but this is saying that, okay, it's about to go kind of like this, and it's going to keep decreasing exponentially. No, it's flattening out to a 0 point, right? There, to a constant point. That's why it's concave up and not concave down, right? Now from this region x2 to x3, there's no forces acting on the block, no acceleration. constant kinetic energy. So now for that, let's think about using the principles of work and energy. Justify the graph for the time interval t equals 0 to t equals t1. Okay. Explicitly reference features of the shape of the graph you drew in part BI. Okay. So let's think about work and energy, I guess. There's really no other way to explain this. I use simple harmonic motion, so I'll use it the same way. So what they want to hear is the spring does nonlinear work on the block from T to, oops, T not to T1 and does not monotonically increase as at, oops, as at T1 Fs must equal 0, hence K or dk dt has to equal 0. But at from 0 to some point t where it's less than t1, there must be POI, point of inflection, as due to simple harmonic motion. So we'll just say due to simple harmonic motion trend, the block goes under. So I'm kind of over explaining it here, but they want to hear that it does non-linear work, right? And they want to explain the shape. So it's not monotonically increasing. So it has dk dt has to equal 0 here because the velocity is unchanging, right? It has to flatten out to where acceleration is equal to 0. But they also want to they want you to explain this part because at some point the spring force is going to be at a maximum, or well, yeah, the velocity is going to be at a maximum because the spring force is going to start decreasing because it's really compressed here, less compressed here, but it's going to start decreasing, right? After the collision, the two-block system instantaneously comes to rest at time t4, which occurs when the spring or the string makes a small angle theta max with a vertical as shown in figure 2. For times t is greater than t4, the system oscillates with frequency FL. The supporting string is raised and the procedure is then repeated using a new string of length 2L. Okay. Oh, my neck. Of 2L. Indicate how the new frequency of oscillation on the system of length 2L will compare to the frequency of oscillation of the original procedure. Okay, so what you need to think, you could derive the period for a string because period is related to frequency like this. So if I can't find frequency directly, I could just think of period, right? You could derive period by using like simple harmonic motion and all that, but I'm not going to do that. I'm going to go up to my equation sheet, look for a little bit. Okay, T pendulum. That was a simple pendulum for small angles. This is, oh my gosh. The period is 2 pi square root L over G. I'll go down and write that as the start to my answer. Oops, I passed it. So I'm not going to answer it yet. I'm going to reason it out here first. So I'm going to say 2 pi square root L over G. So that means L is directly proportional to square root L is directly proportional to T, which is proportional to 1 over F. So hence, if L increases, the frequency must decrease as 1 over F is proportional to T and increasing L increases T. And that makes sense, doesn't it? Right. So, because if I have this T that's increasing and it's like, let's say it's equal to, it is, sorry, it's equal to 1 over F. right? In order to make this number bigger, I have to make this number smaller, because if I'm dividing by a small number like 0.2 as compared to 0.02, I have more like dividends that I can make, right? Which will increase my result. So now that I know that t has to increase, then 1 over f has to decrease. So I'll say F2L has to be less than FL. Okay. So a student drops a cylinder mass m from rest. The air exerts a drag force, F drag, on the cylinder as shown in figure 1. The student models the magnitude of the drag force as F drag equals BV squared. Oh, I don't like that. Where V is the speed of the cylinder and B is a positive constant with appropriate units. Derive but do not solve a differential equation that could be used to determine the speed V of the cylinder as a function of time. Okay, so when you see differential equation and you see drag, you should immediately be thinking, okay, Newton's second law. So let's draw the free body diagram just to figure out what's going on here. So force gravity is pulling it down, force drag is keeping it up, right? So my Newton's second law, sum forces is going to equal, I'll say y, is going to equal Fd minus Fg. Actually, should pick the direction of acceleration to be positive, is equal to ma, right? So now let's replace everything with what we know. Oops. Mg minus bv squared, right? F drag is bv squared, Fg is mg, equals m. Now acceleration is the derivative of velocity. That's where the differential equation comes from. M dv dt. That's it. That's all you need, because they said derive but do not solve. Next question. So the student correctly sketches the speed v of the cylinder as a function of time as shown in figure 2. So draw a vertical line on the sketch of figure 2 to indicate the earliest time at which F drag on the cylinder is equal to the magnitude of the weight of the cylinder. So let's visualize this really, because if it was BV squared minus, or no, sorry, it was mg minus BV squared. So the moment in which these two are equal, right, is when sum forces is going to be 0, right? Because if I take A minus A, where A are the same value, that's going to give me 0, right? So if that means A must equal A, well, of course A equals A, right? Because I just use the same variable. So then mg has to be equal to bv, meaning sum forces has to equal 0. So from this I get this, which means ma has to equal 0, and m is a non-zero number, so a has to equal 0, right? So now, what am I thinking? I have a vt graph, not an at graph, but a is dv dt. So the earliest time at which the derivative of this graph is equal to 0 is when the two are equal, right? Or when terminal velocity is reached. So that's here, right? Because you can see the slope is 0, but here it's non-zero, non-zero, and then it reaches 0. So I'm going to say that's T1. They said label it T1, right? So justify the location of T1. Okay, well, that's what I just explained. When mg equals bv squared, ma equals 0, a equals 0, dv dt equals 0. Done. Rather than dropping the cylinder from rest, the student throws the cylinder upward with a non-zero initial speed. The cylinder is in the same orientation as when the cylinder was previously dropped. The students allow the cylinder to fall toward the ground. Okay. Indicate whether the magnitude of the cylinder's maximum downward speed after being thrown upward is greater than, less than, or equal to the maximum speed Vmax in figure 2. So Vmax, let's just solve for this. I'm going to do my work here. So mg minus bv squared at Vmax, when V is Vmax, is going to equal 0, because when V is max, there's no acceleration. So mg divided by b divided by v equals V max squared, right? So I'm going to immediately click equal to. V max squared depends depends only on m, g, and b, which are constants. Not V naught. Done. And that makes sense, right? Because if you throw something up, right, gravity will do some work, some energy to pull it back down, or it'll do work to pull it back down. But then at that terminal speed where it's at its highest point, the velocity will be zero. So it's as if we're starting with zero anyway, right? That's when force drag starts to kick in. That's when we care about it. So the student conducts an experiment to better understand the relationship between the maximum speed Vmax and the mass. The student collects the data to determine the maximum speed for the cylinders dropped from rest. Okay, dropped from rest, great. Each with the same physical size but with a different mass on. The student then graphs V max squared as a function of mass. Draw a line of best fit for the data. Okay, I need a ruler. I have a ruler. So you're basically just gonna want to line up these points. If they told you in like elementary school, you should try to keep this many points on this side, this many. No, this is physicsy. No one cares. Um, Literally just draw what you think is best. That was not what I thought was best. I have some offset from this ruler. Why is it so offset? This should be better. That's way better. Okay. So there's my line of best fit. And I'll use the line of best fit to calculate an experimental data or value for B. So whenever you see this, problems like these, you're usually going to have to pick points off the graph if it's a straight line. So I'm going to pick a couple points just to find my slope. So 0, comma, is that 1? 0, comma 1. And let's pick another one. You can't pick data points. You can't pick data points. College Board won't let you. They'll take off points if they see that you did that. So I'm going to guesstimate here. That's like 0. Oh, here's like 0.55. So that's, and 0.575, comma, that's like 9.5, like 9.7. So here you have to really derive the equation. So you have to derive why they use Vmax squared. So at terminal velocity, so B Vmax squared, this is what I used earlier. Mg minus that has to equal Ma, which is equal to 0, right? Because A is not changing. So you have to say Mg equals BV max squared, right? So now if it's y, this is my y, this is my x. Let's use our form y equals mx plus b. Okay, well, I have to get my b over here. So this is my slope, right? Or no, sorry, this is my m. This is my slope. X is going to be my dependent variable, is equal to v squared max. So y slope x. Done. So this has to, so I'll calculate my slope, but I have to indicate slope, I'm using so much space, has to equal g over b. That's what they want to see. They want to see that you can linearize it and understand that slope equals that, and which is also equal to, now we're going to start doing my change. So change in y over change in x, minus 1 over 0.575 minus 0. I'm going to use a calculator for this. 9.7 minus 1 divided by 0.575. Cool. Which is roughly equal to 15.13. Right, so now I'll set 15.13 equal to g over b. Well, I can just solve this for b. Well, g is 9.81, so I'll put that in. 9.81 divided by 15.13. So I'll put that in my calculator. Great. So b is oh my gosh. B is roughly equal to 0.65. And what's the unit for that? Well, if this has to give me newtons, then this is meters squared per second squared. What's a newton? Ooh, I'm just gonna I'm gonna use newton squared seconds per meter squared. I just reverse engineered that there because I know if this has to give me newtons and I have like some b that I don't know, like the b unit, meter squared per second squared, well, I just canceled by saying second squared, meter squared, newtons, right? Because that just cancels these two, get newtons. Okay, next question, or next part of the question. Is that okay? The torque questions after this, great. So a student claims that the magnitude of the maximum speed of the cylinder drop from rest depends on the length of the cylinder. The student designs an experiment to collect data that can be used to provide evidence to support the claim. The student drops cylinders with the orientation shown in figure 3. They have access to cylinder set 1 of the same known length, but with different masses, and the same known masses, but with different length. So they want to figure out if it depends on the length. So if the maximum speed depends on the length, and they have a motion detector that can measure velocity as a function of time. So two quantities that could be graphed. These don't have to be linear. I'm going to say V max and length. Plot V max. So they're asking, how could the quantities graphed be used to determine the relationship between cylinder length and maximum speed? So plot V max as a function of, that's a horrible of L if V max changes with L, there is a relationship. Otherwise, no relationship. Done. It's that simple, really. So uniform of rod of length L and mass M. Okay, so of mass M is attached to a pivot on a vertical pole, as shown in figure 1. So uniform rod, so that means it has mass. There's negligible friction between the rod and the pivot. Horizontal string connects point Q on the rod to the pole. The rod makes an angle theta with the pole. A block of mass 3m hangs from the rod at point P, and the center of mass of the rod is located at point C. Okay, it's good that they gave you that. So the rod has mass m. So on the following representation of the rod, draw and label the forces, not components, that are exerted on the rod. Okay, so if 3m is pulled down, this is not moving. That means the force of tension. I'm not going to write force of tension. I'm going to write force of tension is equal to 3m. So I'm just going to write point P F3mg. It's really easy to just keep it that way. So I'm going to say force gravity rod, because this is pulling down with 3mg, right? And this is pulling down with the force of gravity of the rod, which is mg. And then Q, there's a force of tension. That's this way, Ft. And now this is not balanced, but the rod is not moving, right? So you have to account for that in the force of the pivot, which is kind of like a normal force that accounts for all of these other forces. So if I have a vector sum that goes this way and then down this way and then some more, that means my other one has to go right and up more. So it's going to be kind of like this. This is the force pivot. So I'm going to label that F pivot. Now my forces are balanced. Now I can leave it like that. So in figure 1, so we're going to ignore this diagram because that's for the next question. So at figure 1, point P is located 3/8 L from point Q, and 3/8 L from the pivot, and point Q is located 6/8 L from the pivot. Derive an equation for the force tension in the string in terms of L, M, theta, and physical constants as appropriate. Okay, so point P, let's just label that. This is 3/8. Q is 6/8. And C, well, I know it's in the middle, so I'm going to call that 4/8 L. So what they want here, they don't want to sum forces, they want a sum torques, right? Because these are all at angles. I write my tau like this. Sum torques has to equal 0. This is the statement that starts the equation. You need to start it with that. So sum torques is equal to 0, which is equal to the torque due to the force 3mg, right? Actually, we're going to use our right-hand rule to figure these out. So force 3mg is in the negative k hat direction, so I'm going to write negative, and you use that by using the right-hand rule, right? Yeah, if you want, you can Google it, but basically, clockwise torques are negative, counterclockwise torques are positive, minus the torque due to the force of the gravity of the rod, because that's also counterclockwise torque, plus the torque due to the force of tension, which was a positive torque. Oops. So now we're going to write the torques out for all of these. So torque is equal to R cross F. So I'm really just going to simplify these, and I'm going to say, okay, what's the R for the 3mg? If this said this was 3/8 L, then I know my radius has to be 3/8 L. Well, they want to see this, F sine theta. But what was sine theta here? So they want to figure out, okay, this is my radius. My force is 3mg, but what's the theta between the two? Theta between the radius vector and the force vector. So I'm going to redraw the force vector coming down here. Well, this is a 180-degree angle, so 180 minus theta. If I take sine of that, that's just sine theta. Sine theta. So now I know that my torque due to the force that's 3mg is going to give me negative 3mg, and it was 3/8. This is my force, this is R, and this is sine theta, just theta, right? Now the torque due to the force of the gravity of the rod is the same thing, because the orientation of the gravitational of the force due to the gravity of the rod vector is also going to be here. So I know that one has to also have the theta between the two be sine theta. So I'm going to write mg for 1/8 L. Remember, this is my force. This is the radius. Sine theta. Now this part gets tricky, right? Because here's theta, and here's the force of tension. Or here's the force of tension pulling that way. So I'm going to draw this on the side because I ran out of space. So the theta between these two, I'm going to redraw the force of tension because up here was here. I'm just moving it right there. Here's 180, here's theta. So that has to, oh, there's not theta. That's not where theta is. What am I doing? So here's 90, here's theta. So this is sine 90 plus theta. And that's not sine theta, that's cos theta. So instead of sine theta, we're going to write, since that is at 6/8 L, we're going to write plus ft 6/8 L cos theta equals 0. So now we're going to cancel what we can. Here's L, sorry. Cancel L, cancel L, cancel L, cancel 8, cancel 8, cancel 8. So now we get negative 9mg. If you wonder where the 9 came from, okay, 3 times 3, that's it. 9mg sine theta minus 4mg sine theta. Oh, I'm going to set this on the other side. I'm going to move this to where the 0 is, equals negative ft, the 6 canceled, times 6 cos theta. Cancel the negatives, and we're going to add these two since they have like, whatever it is, variables or whatever you want to call it, combined like terms, right? So 9 plus 4 is 13 mg sine theta equals 6 ft cos theta. Great. 13 sixths mg. Now I'm going to divide sine by cosine. Sine by cosine is tan theta equals ft. That's it. Great. The original string is replaced with a longer string that connects point Q to a higher location on the vertical pole, as shown in figure 2. The angle theta, so this is the same in both of these. How does the tension Ft nu compare with the original tension from Ft? So a longer string, intuitively, you should think less tension, right? A longer string, you'll have less tension if you're pulling with the same torque. So I'm going to say Ft is less than, Ft nu is less than Ft, because some torques has to stay 0, right? I'm about to reason this through. And the torque due to 3mg and the torque due to FGR remain constant. Hence, the torque due to the force of the tension also has to remain constant. Now, the theta that was here looked like this, right? But if I'm increasing it to some theta, that sine is going to approach 90, right? So it's going to go from 0 to 1. So this is where 0 degrees, this is 90 degrees in sine. This is for sine, right? So you know how there's components for torque where it's RF sine theta? Yeah, sine theta is increasing now, right? The radius was the same. So that means if this increases and I want to keep this constant, force has to decrease, right? So torque has to remain constant. Theta, theta between Ft and R increased. Increasing, my handwriting is horrible, I apologize. Increasing sine theta. Hence, Ft must decrease to keep the torque due to the force of tension constant. That's what they want to see. That will get you the point. Okay. Next question. A non-uniform rod is now attached to the pivot, as shown in figure 3. There is negligible friction between the non-uniform rod and the pivot. Sorry. The rod has a length of 1.2 meters and a linear mass density lambda of x equals a plus bx, where x is the distance from the pivot and a is this constant and this constant, or b is that constant. So the mass of the rod. So when they ask you to calculate the mass of the rod, you know that these masses have little individual dm's that are not the same, right? So this dm could be different from this dm, right? But they're all little small infinitesimally pieces of dm. So this could have mass here that's m1 and this could be m2. M2 could be way bigger than m1 because it's non-uniform, right? So what we have to do, we have to use integral calculus to show that the distance, or to find the mass. So you have to say integral dm equals m total. So let's see, m total. So then I know that lambda equals dm dx, and this is on your equation sheet if you forget it, but that's okay. So that means lambda dx has to equal dm. They want to see this entire thought process. So I would write this down when you're deriving. So now I'll replace my dm in my integral with my bounds of integration, which are from x equals 0 to x equals 1.2. So from 0 to 1.2, 0 to 1.2, lambda dx is equal to mass total. Well, lambda is a function, so I can't really integrate it just like that. So I'll use integral 0, 1.2, and a was 6 plus 10x dx equals m total. Great. So now I'll just integrate this like normal. This will give me 6x plus 10x squared over 2 is 5x squared from the limits of 0 to 1.2. So m total has to equal, if you plug in 0 to both of these, that will give you 0. So it's going to give you 6 times 1.2 plus 5 times 1.2 squared, which is roughly equal to, put this in my calculator. They want to see the limits of integration, though. They want to see you fully integrated. So I would do that. I think you could use a calculator to just verify your answer, but still integrate, which is equal to 14.4 kilograms. Great. Next question. Calculate the rotational inertia of the rod about the pivot. Okay. So integral, you should memorize this, but it's on your equation sheet. R squared dm. That's rotational inertia. So in this situation, R squared is x. Is there more? Nope, there's no more. So R squared is going to be x because that's my distance from the pivot. This normally would be R, but we can just call it x now. So this is going to be integral, and we're going to sum up all the little dm's from 0 to 1.2 of x squared dm. Well, I said earlier that dm was lambda dx, so I'm just going to replace that again, times lambda times dx. Lambda is not a constant, right? It has x in it, so I'm going to have to sub in what I had for lambda. So integral 0, 1.2 x squared, and this was 6 plus 10x squared dx. So now I'm going to distribute, and I'm going to get my integral 0, 1.2. Oh my gosh. 6x squared plus, oh, this is not squared. Made a mistake. Plus 10x to the third dx. When you integrate that, that yields 6x squared divided by 3, which is just, sorry, 6x to the third divided by 3, which is 2x to the third plus 10 fourths x to the fourth over 0 to 1.2. Now, if I plug in 0 here, it's going to give me 0. So I'm just going to put, I'm just say I is equal to, bring this down to 1.2. We're going to plug in 1.2 plus 10 fourths 1.2 raised to the fourth, which is roughly equal to, I dropped my phone. Why isn't, okay, which should be roughly equal to, let's see, 2 times 1.2 raised to the third plus 10 divided by 4 times 1.2 raised to the fourth, 8.64. 8.64 kilogram meter squared. And that's roughly 45 minutes. So I hope this helped. This is the answers to the full Physics C Mechanics set 1 for your response. I wish you all luck on your exam, and I hope you get that 5. You all have a nice day.